So, like already agreed, we will do this talk in English. There's a couple of guys who are English native speakers, so in order to let them also enjoy the presentation, let's switch to English. Yeah, my name is Andreas. I'm from Nuage Networks. I'm working there as a kind of solution architect, pre-sales, whatever needs to be done guy. This talk is mainly technical, so some of the topics you might seen for the guys who have been in the NSXT session in the Royal 2 room, which just went over. You will see similar slides and similar kind of discussion topics. The major difference is I will also hope the demo gods are with me and we can show a lot of code and we can show a lot of demos on to see it, to go a little bit away from the PowerPoint bashing. Nevertheless, for the guys who never got really in touch with Nuage as a technology, with Nuage as a company, I will do a small introduction, no marketing, in order to have a common scene. So what we want to cover is basically quick intro, then one of the major questions is, okay, why do you need even a platform like Nuage on top of OpenStack Neutron? So obviously, like you see from the topic and like you see from the agenda, we are an SDN company, so adding SDN functionality to the native Neutron stuff. We're talking a little bit on the platform, then we do a little bit of show me the code, which is also then the part of the demo session, and then we do a recap Q&A. Nevertheless, let's keep that interactive as possible, so feel free to shout, to scream anytime, I don't mind. Since already outlined by Tom in the session before, Openstack Networking seems to be one still of the hottest topics and one of the areas which needs a lot of improvement and which needs a lot of understanding, needs a lot of technology background, and needs a lot of potentially even fixing and improvement. So if you look at native OpenStack, and don't mind if you cannot read that, but nevertheless, there's a couple of different elements. Oh, but this resolution is really ugly. Sorry for that. There's a lot of elements which basically gets configured from two fundamentally different elements. So you have more the VM-facing part and you have more the networking-facing part, and both needs to match each other. One is solved from Nova itself, the other one came from Neutron. The problem here in this one is actually that it results in a lot of complexity, because you have a lot of different parts which needs to interact to each other, provide either connectivity on the same compute or provide connectivity between different computes, which results in a pretty complex design, because these are actually Linux interfaces. So if you ever want to troubleshoot that, you basically need to go step by step by step by step and need to check each of the interfaces, and good luck with that. I mean, you can automate it, you can try it, but once you try to find an error inside that, have fun. It will take a lot of time. So the idea we basically came up with, and it's by surprise exactly the same idea which was already pitched 45 minutes ago, is why not try to do this in a single OVS instance. So take an OVS with a native layer 2 function and extend that one by layer 3 and layer 4 functions, and using that one as a single instance. You still have the question on how to program it, how to control it, and what to do on top, but nevertheless, why not having a single instance where you basically map your interfaces from the VMs or from the containers, it's exactly the same technology, into it, but then you just need to orchestrate this single piece and you have a pretty homogeneous data path. From that perspective, you also want to solve a lot of different stuff. Because in this architecture, for all the guys who started with Icehouse and even before, you always had a kind of semi-distributed architecture. And we tried to improve that quite a lot. We introduced concepts like DVR. We introduced concepts like, okay, let's move a little bit of stuff in a more distributed fashion, which works pretty good for most of the layer 2 stuff, even sometimes for some of the layer 3 stuff. But nevertheless, you still had the reliability of a networking node. So for certain functions, either for inter-routing between tenants or for certain functions like floating IPs, it was pretty hard to get it in a distributed fashion. Even if you want to extend that and say, I want to have also full-blown distributed DHCP, that's pretty hard to achieve. And since we decided for that kind of architecture, this was exactly also the focal point where we said, let's try to solve that also in exactly the same way. So this is the more granular flow, even if you want to add external networks and external layer 3 agents. So all the people who had ever set it up that, Nobody worked with come on. Okay, at least 3 guys know what I'm talking about. So what you basically have is a couple of VMs belonging to different tenants. And what you basically want to have is, okay, you want to provide a certain level of isolation. You want to have provide a certain level of, which is a fancy buzzword these days, of microsegmentation. So one of the same compute is not able to the rest of the same compute, but you don't want to rely on networking functions. You want to provide certain functions like external routable networks. You want to break out towards a public IP, and you need a little bit of networking in between. So what we basically do is we providing a single OVS bridge, which is also orchestrated from a controller. What you see here is also the name of this bridge, which is called AluBS0, which is basically based on our history. So back in the days, Nuage was funded by Alcatel-Lucent. We basically said, hey, we need a kind of fancy SDN startup. We as a telecom supplier dinosaur, we cannot really sell either to the enterprise or to the fancy guys, where the money comes from. So we need a new venture. And therefore, Nuage Networks was funded. It's based in Mountain View, so typical US-based Silicon Valley startup. Nevertheless, Alcatel-Lucent itself was taken over by Nokia. So now, these days, we are 100% venture from Nokia. But you still see it from all the branding, from all the marketing, from all this kind of stuff. There's still a kind of independency. Nevertheless, we have a different mothership. You have a different guy who gives you all the R&D dollars. So also a guy who basically set up slightly your priorities. But from the architecture itself, nothing really changed. What actually changed is that now you have a single OVS bridge, which is completely flow-based. And you want to have all the functions, which I talked before, locally processed. What do I mean by that? So typically you want to have switching between the VMs, which is pretty easy to achieve. So you just have 2 VMs sitting on the same subnet, sitting on the same compute, same broadcast domain. Okay, switch in between. Easy task. But what about if you need to route in between? So this guy belongs to subnet number 1, tenant A. This guy belongs to subnet number 2, tenant B. And nevertheless, they might belong to the same project. But you need to have certain interworking with them you want to route. So what you actually want to do in actually old architectures, you break them out, you go to a centralized layer 3 agent, you process all the routing, and then route all the traffic backwards. Which is, from a functional perspective, nice to do, but nevertheless, from a traffic pattern in your data center, it's pretty ugly. Because you actually trombone quite a lot of traffic to this centralized point, and you need to route it there, and then you send all the traffic back. So you spend all the money on the fancy spine leaf architectures, everything is fully distributed, full-blown layer 3 routed, but you're then finally introducing tromboning points to your network. That's not really smart. So why not converting each of the compute in a single router, basically, and let the routing happen directly on that kind of compute? The same is true if you think about netting. You also don't want to have it on a central device just to break out, because all the kind of functions you typically use, like floating IPs, one-to-one NAT, even between different tenants, or you have a public kind of subnet, and so on, you want to have that in a distributed fashion. What you also want to have is things which are more control plane intensive. So for example, if you have a smart control plane sitting on top of all these guys and basically telling your OVS how to behave, why not putting ARP replies and DHCPs and all this kind of stuff directly in the control plane and let the control plane handle it and don't bump the traffic insane around in your data center. Because at a certain point, you want to reduce the bump traffic at all. You want to process it, and everybody should have all the information. So if you think about from a typical control plane perspective, your control plane is already aware. You boot up a VM, you boot up a container, you already know, okay, this guy has a certain MAC address, has a certain IP address, so all the information is already there. There is no real need to bump any kind of traffic and send a broadcast around and say, can you please reply to XYZ? Somebody should answer on behalf and basically tell you, hey, if you want to reach that certain VM, this is your MAC address, this is IP address, let's go. A lot of this kind of stuff was basically also solved in a certain way for DVR. The only problem on the DVR case is a little bit of the source netting and the DHCP issue. For the source netting and the DHCP issue, you still need a central point, and you still need that. So from our perspective and from our design, we even eliminate that one, and it's even fully distributed in Nuage. So If you ever want to connect a typical VM, so this is actually two VMs, tenant A, tenant B, going from the compute to the networking node to the rest of the world. Just the amount of interfaces you would need to going from here to here is actually insane. I mean, if you ever want to process this kind of thing and you want to troubleshoot it, it's really hard to do. And if you think about, since the topic of the talk is infrastructure as code, before you really automate something and before you really take it to the next level, try to simplify it first. It's 10 times easier to basically automate 5 steps rather than 20 steps which are even dependent on each other. So from that perspective, we basically came up with that. So let's use the pointer in that direction a little bit. So actually, you have 2 compute nodes. And what we use is basically a VXLAN in between. The VXLAN is orchestrated by a central controller, and on top of the controller, there's actually a policy plane. I will explain in a second. But now you're facing the problem that at a certain point, you want to go out. And there are different ways how to go out. Either you can say, well, my tenant IPs don't really overlap with my underlay, so why not directly break out? Just route it back to the underlay, let the underlay handle it. It's a routed fabric anyway. Go from point A to point B. That's option number 1. And you can break out on any kind of compute as you want. There is no restriction at all. But on the other side, there may be dedicated gateways where you say, let's bring the VXLAN traffic to this specific point and then break out, terminate it, and then you actually act as a VTAP. In the VTAP, it's quite important that you distinguish between 2 different functions. So what is very common these days, and you find it all over the place, is a layer 2 function. What it actually does, take the VXLAN on one side, stitch it to the VLAN on the other side, and then just send it on the wire. The problem with that is that your tenant IP and the bare metal IP or the rest of the world IP need to be in the same subnet. If that's not the case, you actually need a routing function. This guy actually needs to behave as a default gateway for all the stuff, and it needs to route in between all the VTAPs. So therefore, if you check ever for VTAPs, make sure that they are layer 3 VTAP aware, and you can at least route between all the IPs. Otherwise, you need a dedicated router somewhere else, which burns another CPU cycle, which burns another piece of RAM. On the other side, you also want to have a seamless integration into hardware gateways. So what does it mean by hardware gateways? There are multiple designs how you can accomplish multiple data centers talking to each other or multiple Openstack instances talking to each other and so on. I will not go into detail into that one, but nevertheless, there is always a need to have multi-site deployments. And then you can either say, I want to stretch my VXLAN all the way up and say, go from site 1 to site B to site C. But what you actually do is you expose all the direct next hops from one site to all the other sites. Because for all the guys who are aware how VXLAN works, you're basically setting up a tunnel from this compute to this compute. In order to reach it, you need to know that destination. Otherwise, you will never reach it. And it's a stateless protocol. So if you even have now different data centers in between, you're exposing the entire underlay of that data center to that data center. That's not really smart. If you want to ever scale, you basically create a gigantic routing domain, and therefore more and more people going for dedicated gateways. And then you say, okay, what do I have in between? Do I stick on layer 3 VPNs? Do I do a little bit of VPLS? Do I do everything on EVPNs? That's a different discussion to have. The solution is all about orchestrating this entire piece. So not only orchestrating the computes itself and providing connectivity between compute 1 and compute 2, but also providing connectivity towards the gateway, being it hardware or software. It shouldn't really matter by the end of the day. What's also pretty important, so going back to the compute, a lot of people ask, okay, in order to do all this kind of magic, you need to have certain plugins. You need to be part of the Neutron, basically, code in order to do all this kind of so-called magic. So, and therefore, you had different ways how to do it. At the beginning, you had the core plugins and you had the service plugins. So what we basically came up with back in the days was you have a core plugin and you basically just use it as a mechanism driver and you do a full-blown monolithic plugin, which isn't a real big deal, or at least it wasn't back in the days, because as you saw from the slide, DHCP, IPAMs, all the kind of stuff which you typically put in an ML2 fashion was already fully integrated, even the type drivers. So it's pretty easy to go then with a pure monolithic plugin. Nevertheless, with the rise of telcos, NFV, different types, new VM interfaces, and so on, there's more and more stuff which you need to extend. Either from an pure data plane performance perspective, and this is really hard to read. I mean, wow. Which is either you want to have different ports, you want to have different subnets, or you even go into the full-blown NFV world and you need to support things like SRIOV, DPDK based off workloads, and you need to go from A to B. So basically, we decided to support at a certain time both and say, okay, I want to have either the monolithic plugins and for the guys who want to add their own flavor, or we need to change. You also get a full-blown ML2, and now you also support ML2 plus extension drivers. So for example, if you want to hook up Ironic and you do a fabric provisioning directly out of the SDN layer, you can do that as well. These are basically all the integrations we support as of today. So as you know, from an OVS perspective, there's always the concern, hey, does it really scale? And do you get all the packets? And do you achieve wire rate? And how much CPU cycles you burn? And so on. And yes, back in the days, this was a major, I wouldn't say issue, but you need to work on. And you need to improve your code quite a lot in order to get 10 gig out of a 10 gig file. Nevertheless, you have different opportunities also in the Nuage platform. So the piece of software we actually run on top of the compute is the VRS. It's nothing else than a user agent daemon which sits on top of the OVS kernel. So nothing has changed on the compute itself, plain OVS. But you obviously want to have a different API, so you change just the user agent on top. So there you obviously have a regular Word I/O. You can also have a DPDK version of it. As everybody from which goes to the DPDK path, it just requires dedicated cores. So you need to be aware of what you're actually doing, but you get all the performance you really need. The same is true for SRIOV. On the SRIOV side, most likely you combine it with dedicated switches, dedicated gateways, those kind of stuff in order to get all the performance. You actually punch out the traffic towards a certain interface sitting in your fabric. Then you can also do certain offloading functions. There are two famous, I would say, ways how you can do it. So the most common you see these days, you just push it to the NIC. There are certain vendors, I think the Mellanox guys did a pretty good job in order to do OVS offloading directly in the NIC, and the same is true for Netronome. And there's a couple of other vendors who go exactly that same route. The question is more now, you are not really that independent on your choice of hardware anymore. You need to do a certain bet, and you need to check the vendor you choose, either for your compute or dedicated for the NIC, what is actually supported and how much bandwidth, IOPS, and so on you really want to pass through. And then the last one, which is basically a hybrid of different technologies where you combine FastPass, DPDK, plus OVS, and so on. Then you have even more higher dependency on the hardware itself, but for a lot of use cases, especially in the telco world, where the guys basically want to push out multiple 100 gig to such a fabric, then you need this kind of functionalities. So what do we actually do on top? So now we discussed a little bit what do we do and what do we have. Nevertheless, so on one side, you basically see what is OpenStack default. So what do you get out of OpenStack as of today? Either it's a distributed model for switching and routing, or you have a more centralized model, for example, for source netting, FIP, on layer 2, layer 3, and all this kind of stuff. What you see on the other side, and I don't want to go into each of the details, is basically a lot of the functionalities we added on top. So there are certain things which you just need in certain scenarios and makes a lot of sense. One of the most important things, and I think this is a missing gap still in OpenStack itself, is, for example, real basic things like service chaining. You just want to make sure that if VM1 talks to VM2, it needs to bypass a firewall. And it shouldn't matter if this firewall is now virtualized or if it's a physical gateway. You just need to redirect the traffic to this certain interface, and the interface needs to accept it and need to send the traffic back. Not depending on any kind of routing decisions, not depending on any kind of policy-based routing. It sounds pretty easy. Nevertheless, this is something you don't get out of the box in OpenStack at all. Which is, for a lot of enterprises, especially in the financial industry and especially in, at a big certain size, it's a big issue. What you also want to have, for example, is a direct integration into existing layer 3 VPNs. So not only talking BGP natively and just distribute the routes, why not setting up even VRFs? And why not taking care that all your route targets and route distinguisher directly match the configuration on the provider edge, which is pretty important. You also want to have certain things like traffic mirroring, so saying every traffic who add or who enter a certain VM, who goes out of a certain VM, why not writing directly a PCAP file on the fly and send it to a centralized logging base? Then cross-tenant routing, which is pretty important. So you have different tenants and you just want to route between them. Having shared domains, and which basically means, okay, there is one subnet, and every tenant, independent of his Openstack relationship, is able to reach it. A lot of guys need it, for example, if you want to share certain services like Pixie Boot or whatever, DNS infrastructure, which is totally common for everybody, and you can subscribe to it, but nevertheless, you want to provide all the microsegmentation and isolation functions on top. And then you see a lot of routing options where you basically say, I want to have dedicated routing, either to the underlay, I want to do PAT instead of NAT, and all this kind of stuff. So this is typical functions what we do on top. How this platform actually works. So, like pretty common these days, you disaggregate all the typical functions you have in every stack and give it a dedicated form factor. So what you typically have, you need to interact with the platform somehow. So you need to have a management stack, you need to have a policy engine, which is in the Nuage terminology called a VSD, so Virtualized Services Directory. And this is nothing else than your single API endpoint. So this is where all your calls you place to, and this is how you interact with the platform. It's a single API, fully RESTful. You can have it also in Python, you can have it in Go, you can have it in J. It doesn't really matter. It's just an API. Nevertheless, under the API, you have your controllers. So what you do is, you inside the API, and there's also a GUI, and there's a representation and all this kind of stuff. You take your intent, so you design your network intent, you're creating subnets, you're creating FIPS, you're creating everything you really want to have out of the platform, you're creating inside there, and then you subscribe to it, and then you're talking towards the controller, which is called Virtualized Services Controller via XMPP. XMPP is just a chatting protocol. So take the intent, bring it down to the controller, and talk about it. And since you need to scale, and you might have a lot of these controllers, depends a little bit on your architecture. A lot of people intend to do at minimum 2 controllers per availability zone. There is no real blueprint design. It depends on your OpenStack design. It depends a little bit on how far you stretch your OpenStack. Do you have a dedicated cluster per data center? Do you stretch clusters across multiple data centers? Do you have inside one data center multiple clusters? So there's a little bit of discussion which needs to happen in order to design it really wisely, because otherwise you might introduce a really high availability SDN solution, but your OpenStack cluster is a single point of failure itself. And what is very important is you have a single fabric underneath. So your controller actually talking to multiple hypervisors. And as you see also right here, which is one feature out of the platform, is it's not only a solution which supports KVM for OpenStack. You can also do exactly the same for ESXi workloads and integrating into vSphere. You can do the same for Microsoft with Hyper-V, Azure, and those days. You can have it for Zen. And last but not least, which is pretty common these days because you need it for Kubernetes and so on, is you need an integration into any kind of container frameworks. What you also see very often, and this need is driven from a lot of enterprises. So what we see with our clients is not everybody has full-blown virtualized everything. There's not a single customer where you basically walk in and say, everything is virtualized, everything is on VMs. There's at least a little bit of storage, which needs to integrate it somehow in the OpenStack cluster, which is not really part of it and not SAF yet. There's most likely at least different hardware load balancers which needs to be integrated and then needs to be reached. There's very often dedicated physical firewalls, which are just there as a perimeter security which you want to integrate. So you see there is a need, basically having the communication between all these different computes being able to talk to this kind of bare metals. And this bare metal is not really a bare metal. It can be also a physical firewall because it's not aware of any kind of virtualized technology around it. It doesn't, from the bare metal perspective, it simply doesn't exist. So what you typically do is you place your VTAP, again, virtual tunnel endpoint for VXLAN, directly in front of it. And what you need to be able to do from a platform perspective, being able to talk to this switch. Because most likely either it's a Cisco, it's an Arista, it's a Cumulus, whatever, Dell, something like that. So being able to provision that switch to acting as a VTAP, absorbing all the traffic, applying policy, applying quality of service, applying statistics, and then basically let that bare metal be part of the overall framework. And then what is very important also is now you have solved it for your entire data center, but very often you need to talk to the rest of the world. There is more data center than one. So you need to take into account that you also want to provision data center interconnect directly from the platform, and you want to establish EVPN connectivity. More technical, so everything is based on EVPNs. Why EVPNs as a control plane? Well, you have the beauty that you can route layer 2 and layer 3 information in exactly the same control plane. There is nothing which you need to develop on top. And you can have different dedicated route types, like for all the people who are familiar with EVPN, using route type 5, so you can do everything you want. Layer 2, layer 3, giving policy, giving metadata. You can even extend it. So all the tags you basically have on your VMs, so calling one VM red and calling the other one yellow. You can translate in community tags into BGP, transfer it to the other side. Everybody needs exactly what yellow and red actually means, convert it back to policy rules, and you can apply your policy. So since this talk is actually infrastructure as code, now we finally go to the code part. We are pretty much involved in a lot of projects. You see, so one of our prime integration partners is Red Hat, because yes, you can do a lot of stuff upstream and pure open source. Nevertheless, you see that a lot of enterprises also picking up distros of Openstack because they want to have a certain management of SLAs and they want to have a certain management of capabilities. So it makes sense for us also to work with those guys together, especially in the deployment tools area. So basically, everybody's searching for the magic button solution. Just pressing a button and the entire platform rolls out itself. And there's, I mean, Ansible made a lot of progress to go exactly that route. But nevertheless, you need to also know how you edit your YAML files, and you need to know how to feed actually Ansible. It's not like, okay, this is my data center, press the button and it will roll out. It will not gonna happen. And the same goes for SDKs, scripting, and so on. So there's dedicated GitHub pages, there's blog posts, and so on. So there's a lot of code which you can basically grab. What's also pretty important, and I will have a small demo of that one, is a lot of people ask, hey, now I have a feeling of this SDN platform and I know slightly what it can do for me, but I just need a runtime. Where can I get a dedicated runtime on the fly and just boot it up, give me a couple of computes, and I just want to play around a little bit. Therefore, we have something which we call Nuage X. Nuage X is actually a cloud-hosted controller, a cloud-hosted management plane directly on Nuage premises, and you can add your own compute to it. You can have your own OpenStack cluster just mounted to the controller in the cloud, and you can play around with it. There is a dedicated alias, so you can even subscribe to it, which is called Open Community. So everything, all the kind of upstream commits, we do all this kind of stuff. You see it right over here. And for all the people who followed us a little bit, obviously we are quite active also on different OpenStack summits, KubeCon, DockerCon, so everything out of interest where you see presence, or even the German OpenStack days. So going back to the API world, I mean, this is pretty easy. You have a user, you have an API in between, and you basically, as a user, always interact with this VSD. You can have a multiple cluster of VSDs, which actually means you have multiple instances, load balance itself, and so on. But nevertheless, the important thing is it's a single API call. You just talk to the API, you give your intent, what you really want, and then you basically can provision it. What is also important is we have a lot of abstractions built in, which don't really exist in OpenStack at all. So what do I mean by that? For example, we have something which is an organization. Organization is a single tenant which can belong to X amount of different OpenStack projects, but you can totally route it independently. Everything can totally overlap, and there's no one-to-one mapping. And the same we do also behind that. Then we have what we call a domain. Domain is obviously a kind of layer 3 abstraction. Think about a domain like a VRF in layer 3 routing technology. So you group together certain elements and you can route them in the entire world. But what you also have is a zone. Zone is nothing else than a logical group of subnets. Because for the people who are pretty familiar with firewalling technology and security, firewall guys like to build zones. So they group together certain elements, most likely subnets, and then you can treat them. Why we have all of that is you can write a policy against this entire tree. So you can say, I want to have a certain policy which goes from a certain source, which can be either a domain or even an organization, down towards a dedicated vPort. So whatever comes out of that domain, which can be a gigantic amount of VMs, which can be a gigantic amount of containers, especially to that kind of port, treat it, either allow it, deny it, or whatever. Also, what is very important if you set it up the first time, the entire platform is default deny all. So if you just set it up, you boot your computes, you boot your VMs, you boot your containers, and you want to send just a basic ping from point A to point B, nothing will gonna happen. You need to write a dedicated policy to even allow pings and ICMP and all this kind of stuff to let traffic happen from one side to the other. You can make your life pretty easy and just deploy a policy any allow all. Fine, but that's not what you do normally in real life at all. What is also important for a lot of people, how do we actually integrate into a common CI/CD stream? So this is really the entire flow. So where you have the Scrum, you have your IDE tools and so on, and you see also here certain examples, for example, for source control, GitHub, GitLab, Bitbucket, whatever you name it. You can add your own stuff on top of that, and you can have your continuous integrations. I think in the last demo from the VMware colleagues, he used an example with Packer, but you can do whatever you want. There is no real restriction what kind of tool you really want to use by the end of the day. But what you have actually is something where you break out after the continuous integration into the continuous deployment, because this is actually the point where you have your defined image, you have certain properties associated with the image, and now you finally need a network. You need an abstraction to deploy that VM, container, code piece into it. So you go to your platform of choice and say, give me this kind of construct, which can be 1 subnet, 2 subnets, 3 subnets, 1 rule of security, 10 rules, 20 rules, 50 rules. It shouldn't matter at that point of time. And then you basically go out and then you have different options, which is nothing else than either configuration management and so on. You can either say, I want to provision it via dedicated Go, I want to go via Ansible, I want to go via Puppet, I want to go via Chef. It shouldn't matter at that point because you give an intent towards the API and say, take this kind of intent and do something. And I will show it in a minute how this actually works. Here we are. So let's see. I hope the demo god is there and I'm still online. So let's start right over here, which is actually the so-called VSD. Looks good. But this resolution is most likely killing me. So what you have here is one thing which I just called an OpenStack default. It's nothing else than you define something in OpenStack, and inside OpenStack, it will pop up. But before we go into that route, what I actually did, and this is my test. I'm not sure if you can see that. So it's a basic environment. You have an OpenStack controller, you have 2 OpenStack computes, you have a software gateway, you have a little bit of BareMetal to play around, you have a single controller, and you have a single policy engine, you have a jump host to jump in, directly hosted in the internet, I can access it from all over the world. What I basically did is jumping to the OpenStack controller and just say, which is actually here, and just say, okay, take this kind of keystone file because it gives me certain right, and then just start to provisioning certain networks and certain subnets. So pretty easy stuff, right? And as you see here also, it's a directly native Neutron API. There is nothing, I mean, this guy is not even aware there is Nuage integrated at all. It's a native API call and say, just create me this kind of network. So he creates the networks, and after the networks, you're creating all the subnets and integrating some kind of gateways. And once you are done, you're actually adding all the interfaces to a router. I took my life easy and just called the router gateway Openstack. And once you are done with that, you basically grab all of your networks, taking the ID and just booting up via Nova calls a dedicated VM inside this kind of security, with an assigned security group. So nothing fancy at all, not SDN related at all. And I mean, we can spend hours on how to automate this part. You can use Terraform, you can use Heat, you can use different API calls, but that's not really focus of the talk here. The focus is more in, once you have that, or how you can either change it, manipulate it, and cheat around. Because what actually happens is, inside OpenStack, he goes in and basically says, oh, I haven't even changed it to English, sorry for that. Here we go. So once you have that, you see all the different networks popping up here. So you have the Dev OS, Firewall OS, Data OS, and App OS. And what actually happens from an SDN perspective, you have two different ways of integration. You can either say, take whatever is in OpenStack, pull it back to SDN and just fixing all the layers, and import it directly. So what happens, it will look like that. So you see here, this is the Gateway OS. Inside the Gateway OS, come on. You're actually building two zones. What you also see here is this yellow marker right here. The yellow marker just indicates, hey, this is driven from an external authority. So somebody in OpenStack provisioned it. You cannot really change it. It's just directly imported, and it belongs to the control of OpenStack. So you're picking up all the UIDs. You're picking up all the names. Like, for example, these are the UIDs. These are all the names. And then you see all the different interfaces, because you're booting up all the VMs. And what you result to by the end of the day is something like that, where you have all the different VMs, and it's pretty easy. It's just per instance 2 VMs to play around a little bit, and then do later on also things like segmentation and so on. And you have 2 VMs from app, 2 VMs from dev, 2 VMs from data, 2 VMs from firewall. What's also pretty important is, now at that point you can start to play around, because I just imported the default security rule, and at that point he basically says don't allow anything. So if you now go to policies, which is also a different way versus OpenStack, so we distinguish between ingress and egress. You can write ingress policies and you can write egress policies, which is different than native OpenStack. You see that guy? So that guy has, again, this orange mark and says, this is the external default security group. And you basically say, I don't want to have any kind of traffic allowed, and so on. I wrote this one, just allow all, to make my life easy, and which basically says, allow all the traffic, ingress, egress, from any to any. So what you can do now is, let me check where I have this guy. I think it's no. I think it's right over here. No. Lazy. Okay. So this is actually the public IP of my jump host. So if you go back to the demo, here we go. Then you see here all the IP addresses. And that's the public IP of the jump host. So exactly that guy. So jumping on the jump host. And what I also added, because for remote demos, normally the VNC client and all the console connections pretty much sucks. So what you actually do is, you go back and say, inside the design, I used one of the ports, which is from the firewall, and I just assigned a floating IP. What actually means I want to reach that guy directly from my jump host in the simulated underlay. Why do I do that? Because if I click inside here and say, give me the console of that guy, it's pretty lacky and it takes a lot of time and so on. So actually, I want to have a dedicated fib also into that one. So I jump into here, and I'm directly connected to the VM, which is the 13.13.13.2. Going back to here, which is my firewall VM. So now I have my allow all, which basically means I should, with no change at all, I should directly being able to reach the 12, what was it? I think it was 3. So here we go. So you can have basic connectivity at this point of time. But now at a certain point, you basically say, ah, shit, this was not the intention. You basically say, okay, now I want to do it the other way around. I don't want to use the direct OpenStack API. I want to use somebody who has a predefined networking architecture, which you are just being able to consume out of OpenStack. So, which is also a pretty much use case for a lot of guys. So what we actually do is here, we're just adding a subnet, which let's call it FUBA. Let's make it whatever, 15.15.15.1. We need a gateway. By the way, you can do the gateway wherever you want. If it's the .1, it doesn't matter. It can be the 100, it can be the 200, it can be whatever you actually want. So there is a mistake, and obviously create. So what actually happens is now you see you have this newly created subnet. If you're now going here, well, nothing really changed. So where is this damn subnet? It doesn't exist in OpenStack at all, because you actually just provisioned it in the SDN layer and you don't really give the right yet to OpenStack to consume it. So what you can do, you're basically going in and say, okay, I know there's something sitting here and I want to have this subnet. So there should be something, there should be something. And these are just the IDs giving up from the prior OpenStack installation. And now you see here the FUBAR subnet actually shows up. But the major difference is, if you see here, you cannot change anything. All the IPs, everything is totally pre-configured, which is more an use case where you have certain users which are just able to consume network resources, even in OpenStack, which are fully predefined, which is sometimes a better way to basically teach your users and give them a certain way how to behave, because sometimes if you don't really control who's onboarding on your OpenStack cloud, it can go really wild. So now to even show that we can use this kind of guy, let's just start an instance in this actively new FUBAR client. In this new instance, we make it pretty fast. Here we go. Just want to have it tiny. And I want to add it in FUBAR. Here we go. So now this guy is booting up. He picks up the 15.15.15.2. So if I'm now going back to my jump host, 50. Ah! Oh. What? What the hell is this? Wow. This looks weird here. So actually, what we actually just did is we created a subnet in the SDN, imported it towards the platform of OpenStack, booted up a VM inside OpenStack, and basically say, okay, now make this guy reachable. So what we can do now on top, and this is now the more cooler part, is actually, if you look here, like I said before, we have certain domains which exist, we have certain abstractions, but now I just want to start something totally from scratch. So what I did here is, it's nothing else than a Python script which grabs a certain YAML file, and inside the YAML file, you just define certain abstractions. So if you look at the YAML, it's pretty easy. You give it a little bit of help. housekeeping data and say, this is your point where you reach, this is your usernames, and so on. And you can even do that fundamentally different. You can even import certs, you can do cert-based authentication. It was just quick and dirty, to be honest. And what I wanted to have is just something which I call API with a certain domain. I want to have a couple of subnets in between, and I want to have certain ACLs, which says, okay, recheck that, build an ACL which protects against ICMP, but let all the rest of the guys basically talk to each other. The idea behind here is you have a human readable abstraction, which is YAML in that point. It's exactly the same stuff which you normally use with CNI for the guys who are more from Kubernetes land and are normally used to that one, because this is how you define networking in Kubernetes these days. And you basically go in and say, okay, take that one and say, just provision that. And he now fires up a certain amount of requests going out, and like I said, you can have it in Python, you can have it in Go, you can have it whatever you want, but you basically take all those kind of information and putting it up, and let me and if you look, this is actually the entire script. So if there is certain interest, I can send it around later on, but it's less than 350 lines of code. So it's not that much, but and there's a lot of stuff to parse YAML and reg parse and so on, but it's not that complicated at all. Nevertheless, going now back to the UI here, a major thing changed, because now you see this API guy popping up here, you see the domain popping up here, you see all the subnets, and now you can directly import certain VMs. Plus, there's a certain extension to that one. You can even say, going up for A, now I need to be fast, where you basically say, show me the policies, and here, at this point of time, there is nothing. Now you see an egress policy, you see an ingress policy, and you even write certain entries to it for certain protocols. And like you see here, you want to have port 22 for SSH, either deny or blocked, and you can build an entire infrastructure based on any kind of code snippets or abstractions. And now I think, if I'm not misleading, I'm already 2 minutes over. So quickly switch to the recap slide and conclude. So ta-da. So again, Nuage is basically providing you a platform which allows you to provision hardware vTabs, physical server, virtual machines, containers, and even public cloud. So we didn't really touch the public cloud PTS. It's a dedicated session on its own. Nevertheless, if you want to try it out, just go to Nuage X. You can use any kind of public cloud of your personal reference. I'm a big fan of Packet.net. It's really cheap and easy infrastructure. Works pretty good. But you can use whatever you want. Reach out to us, talk to us. We are here the entire full days. You are a quiet crowd, I see. Not much questions at all, but feel free. Thanks.
Okay, any questions?
Can you run on any hardware?
Yes, it doesn't matter. Because like I said, it's either part of the OVS, which is anyway part of the OS system. From an hardware VTAP perspective, it can be an Arista, Cumulus, whatever. Yes, you need to have certain interfaces like OVSDB or EVPNs. But from a hardware perspective, it doesn't matter.
What's the difference between this and VMware NSX? Wow.
That's a good question. It depends which kind of flavor you see from NSX. I mean, obviously, you need to check if you compare it with V or T. So a lot of things you need to take into consideration is what kind of modules and things run either in kernel or in user space, or for what kind of functions you need a dedicated VM. In ESXi mode, to be honest, we need to do all the magic in a dedicated VM, which runs on top of the ESXi host. So it's not 100% kernel integrated, versus NSXT, for example, is. But let's talk about that offline. Any more questions? Thanks.
Thank you.